Can we actually take a tangent on a tangent on a tangent on a tangent? How old is the universe? Can you dig in onto this number? How do we know currently with those? I guess you said 4 or 5
significant figures,
significant digits.
So we can come about it from 2 different ways. One, basically, they rely on the most important number in cosmology, which is called the Hubble constant. The Hubble constant is this weird number that has the following units. It has the units of kilometers per second per megaparsec. So it's a speed per distance, which means you multiply it by distance and you get a speed. And what is the speed you're measuring? Well, you're measuring the speed of a distant galaxy at many megaparsecs away. So a galaxy at 1 megaparsec away, this isn't actually strictly true because of local gravitational effects. But if you go out, say 1 megaparsec away, I would say that galaxy is moving 72 kilometers per second away from you. And every galaxy, except for the very most local group surrounding us, maybe a half a dozen galaxies, out of 500 billion galaxies to perhaps 1 trillion galaxies. So 12 out of that number are moving towards us. The rest are moving away from us. So that number, if you invert it, if you say, well, when did those things last touch each other, all those galaxies? Now they're really far apart. We know how fast they're moving away. It's a very simple algebra problem to solve. When were they touching? That's where you get that number from.
So there's the local 12 and then the rest.
Ignore the 12, yeah.
And then ignore the 12 and then look at the others and then solve the algebra problem. How does the stuff in the beginning, the mystery of that beginning epoch change this calculation of?
Very little, because actually we understand how there's some other ingredients that go into it, namely how much dark energy there is in the universe, how much dark matter there is in the universe, how much radiation, light, neutrinos, et cetera, there are, and how much ordinary matter, like we're made up of, neutrons, protons, croutons.
It appears that the universe is bigger than it is older. How does that make sense?
Yeah. So you're talking about the fact that we can actually see stuff in our observable universe that's located at a distance that is farther than the speed of light times the age of the universe.
Yeah.
Naively, you would say that So you're right. If the universe were static, if the universe came into existence, and you can conceive of this, the universe came into a big bang in a fixed universe. So the universe just started off. Those galaxies were, they could be moving towards us, away from us, who knows? That you could say, I can see a galaxy that's at a distance of only 13.8 billion years times the speed of light. That would be true. But the fact that the light is expanding along with the expansion of the universe. So imagine there was some very distant past. We were near a galaxy. It's going to produce some light. And that galaxy is going to be moving away from us. The light's going to be getting more and more red shifted, as it's called. And it's going to be moving farther and farther away from us as time goes on. There'll be some acceleration as we get into the era of dark energy. The light signals, there'll be some cone of acceptance, if you will, from which represents all the events that we could have received information from. We can't currently communicate with that galaxy. It sent us some light, and now it's moving away, and it sent us some light. And because the space is also dragging the photons with it, if you like, the photons are being participating in the expansion of the universe. That's why they're redshifting. That we can see things out to where the universe first began expanding, not just when it began existing. And because the universe has been expanding for 13.8 billion years with no sign of slowing down yet, which is a huge surprise, serendipitous surprise, that we can see things approximately 3 times the age of the universe away from us. So we can see, let's call the age of the universe 15 billion years, just to make the math simple. We see things at 45 billion light years distance in that direction. And we see things at 45 billion light years in that direction, just turning our telescopes 180 degrees away. So that means we see things that themselves are 90 billion light years away from each other. That's sort of the diameter of the observable universe. Is there another universe beyond that? We don't know. Some conjecture there's not only one, there's an infinite number of them.
How are you emotionally okay with the fact that our universe is expanding? So
it's going to be like Annie Hall, like with Alvy Singer.
I grew up in the Soviet Union. We watched propaganda.
I realized that you did, yes. So there's a famous
Annie Hall. Is that some kind of what is this?
Party propagandist movie with Woody Allen. Certainly canceled, but nevertheless, back when he was not canceled yet, he made a movie called Annie Hall, in which it's a self-depiction. He's like a Larry David before Larry David was Larry David. Typical neurotic young Jew. He's in Brooklyn. And he all of a sudden tells his mother he's not doing his homework anymore. He refuses to do his homework. His mother says, why? He goes, because the universe is expanding and it keeps on expanding. Everything will rip apart and we'll never have anything in contact and everything is meaningless. And I assume these are some of the topics we're going to get to. And she goes, what are you talking about? We're in Brooklyn. Brooklyn is not expanding. And that's true. Brooklyn is not expanding. The solar system is not expanding. Oftentimes I get asked, what is the universe expanding into? That's one of my favorite questions. What is it expanding into? And I say, it's actually an easy question if you think about it. You've seen your friend Elon, he goes out into space, he's got a rocket, right? What's outside of the rocket? If you take this bottle, empty out this bottle, take the cap off it, go outside the rocket, sipping some Tang, screw on the cover of it. What's in there? Is it empty?
That's just semantics, I guess. Yeah.
No, it's definitely not empty.
So you step outside the rocket?
Yeah, you're in the vacuum of space, the quote-unquote vacuum of space.
And there's no more liquid in it?
There's no more liquid in it. No, it's just a container, 1 cubic centimeter. Let's just make it simple. 1 cubic centimeter of box, and you take it out into space, outside the Falcon, whatever, right?
Yeah.
What's inside that box? It's not empty. There's actually, I'm going to say, this is going to set your friends up. There's 420 photons from the fusion of the light elements that we call the cosmic microwave background inside that box at any second.
Okay. All right. Hold on a second. What? 420. That's, I've heard of that number before. All right.
It used to be 69. But then they changed it.
Wow, physics works in mysterious ways.
In a millimeter box, it's 69.
What are we talking about here? What's in what's in the box?
I'm gonna get that's right. Let's think outside the box. No, we're thinking inside the box. So if you have every cubic centimeter of our observable universe is suffused with heat left over from the Big Bang. Dark matter particles. There's a little ordinary matter in the universe. And every cubic centimeter, there's some probability to find a proton, a cosmic ray, an electron, et cetera. There's actually an awful lot of neutrinos inside of that cubic centimeter. Now, just imagine how many cubic centimeters there are in the universe. It's enormous. That's why there's enormous numbers of particles in our universe. It's a very rich universe. But now let's zoom in on that box. So now inside that box, there might be, one, let's say there might be one ordinary matter, like a proton or an electron, a baryon, a lepton. There might be a couple hundred neutrinos, and there'll be a couple hundred photons, as I said, 420. What's between those guys? What's between the protons and the neutrinos and the photons? Like, just zoom into a cubic micron now. Like, imagine 420 things inside a box this big. It's actually pretty empty. Mm-hmm. Like, they're just zipping around in there, right? So between them, there's a lot of empty space.
And this is outside the kind of physics-based models of fields and all those kinds of things.
Yeah,
just actually asking the question of, like, what is this emptiness?
What's the particle content in the universe in every cubic centimeter of the universe?
Outside of the 420. So you have the 420.
Yeah. 420.
They have some, they have some mass.
Yep. Oh, they have the energy. They don't have mass. Photons don't have mass.
Energy.
That's why they don't bring
mass.
suitcases. That's true, right? Photons never bring suitcases with them because they're traveling light. See, I don't even get a laugh out of you.
That's
corny dad jokes. Okay, you'll appreciate it sometime.
No, this is pretty good. It's just I'm laughing on the insides. What's in the box? What's the 420? What's between the photons?
That's what space is. That's what the universe is expanding into.
Okay, that's
nothing.
So that's the notebook
on
which the photons are written.
Exactly. That's beautiful.
But still, thank you. Still, I understand this, but it's still uncomfortable that if the universe is expanding, that this thing is expanding. The canvas is expanding. It's very strange. Because like if we were just sitting there still, I guess if we're in Brooklyn, nothing's expanding. So our cognition, our intuition about the world is based on this local fact that we don't get to experience this kind of expansion.
Yeah, and that intuition leads us astray. But that gravity is the weakest of the so-called four fundamental forces. And yet it has the longest range pervasiveness. Gravity is, we're being pulled towards the Andromeda Galaxy at some enormous rate of speed because of its massive counter-gravitational force to the force we exert on it. So gravity is enormously long range, but incredibly weak. And because of that, we can think about these effects of expansion as the relationship between as you said, the grid lines on the notebook, right? Gravity is a manifestation of the interrelationship between those points, how far they are from each other, and those can change. Those point distances can change over time because of the force of gravity. So it's weak, and what we experience as gravity is the changing of those trajectories from being rectilinear to curvilinear. That's what we experience as gravity. Well, you had this analogy when you talked to Barry Barish about a bowling ball and a trampoline. That's almost right, because it's actually, you have to visualize that now in 4 dimensions, like wrapping a trampoline at every point around the object, including on the sides. And it becomes very hard to visualize. So a lot of people use that. It's also a fraught analogy because you're using gravity, like the notion of gravity pulling something down, to explain the notion of gravity. So it's a little overburdening the analogy.
Mm-hmm. But okay, so you mentioned Barry Barish wrote the foreword to your book.
Yeah.
How do gravitational waves fit into all of this? How do they, on the emotional level, how do they make you feel that they're just moving space-time?
Yeah. So gravitational waves were the Nobel Prize for gravitational waves discovery the first time. It was discovered twice, indirectly by 2 men named Hulse Taylor. And that was given my first year of graduate school. The day I entered graduate school almost, they announced these 2 guys won it. And the guy who won it did the work that would later win him the Nobel Prize when he was my age.
Is this in the 40s?
This is 19.
That was a joke.
Yeah, that was good. Right. That was good.
Thank you.
I got it. To a cosmologist, age means nothing. Yeah. And to a tennis player.
Not on Tinder.
That's right.
All right. Sorry.
Gravitational waves do fit in because what we're trying to do now is use the properties of gravitational waves, the analogous properties that they have to photons, that they travel at the speed of light, that they go through everything, they can go through everything, and that they're directly detectable. We're using them to try to confirm if or if not inflation occurred. Mm-hmm. So did inflation, the spark that ignited the fusion of the elements in the early part of the universe and the initial expansion of the universe, did that take place? There's only one way that cosmologists believe we could ever see that, through the imprint of these primordial gravitational waves, not these old, newcomers that Barry studies, the ones that occurred 1 billion light years away from us, 1 billion years ago. But we're seeing things that happened 13.82 billion years ago during the inflationary epoch. However, those, we cannot build a LIGO and put it at the Big Bang. So if you want to measure, let's say you have the old-time firecracker. Let's say there's a firecracker, and you want to see if it went off in the building next door to you. You can't see it, so you can't see the imprint of it, but you can hear it. And what we're trying to do is hear the effect of gravitational waves from the Big Bang, not by using a camera or even an interferometer like Barry used and his colleagues, but instead using the CMB, the light, the primordial ancient fossils of the universe, the oldest light in the universe. We're going to use that as a film, quote unquote, onto which gravitational waves get exposed.
And hope you can. So, what are the challenges there to get enough accuracy for the exposure?
So the signal, as I said, is so there's 420 of these photons per cubic centimeter, and there's a lot of cubic centimeters in the universe. However, what we're looking for is not the brightness of the photon, how intense it is. We're not looking for its color, what wavelength it is. We're looking for what its polarization is.
And we'll go there. Let me just ask, are you serious about the per cubic millimeter? 420 is the number?
Centimeter.
But cubic centimeter.
Yeah.
420 is the number.
That's the number.
I wonder if Elon knows this, and if he doesn't, he will truly enjoy this.
Okay. This is great. Yeah, it's true.
Oh, okay. Funding secured. Excellent.